Today we're going to be looking at how to do volumes of solids of revolution using double integrals. And we're going to do it by looking at this question here, which is a great question because it involves revolving around both the x and y axis. In fact, this is a question we've already done using the more traditional disk method, and you can have a look at that video in the there's a link to it in the description to this video. But anyway, what we're going to do here is let's go from first principles on double integrals as to how we can solve this. So basically what we have, I'll tell you what, let's just keep the question. I know we haven't got room for the question. So basically here is the y-axis and the x-axis. Here is the line y equals x. Here is y equals x squared. And basically we have this region here, and we have to rotate it around both the x and the y, and what the question asks is what is the difference between those two volumes of solids of revolutions. And what we're going to do this time is we're going to look at double integrals, and how double integrals work is what we're going to do is we're going to take a little tiny square there, which is going to be width dx and height dy, and what we're going to do is we are going to revolve that square around for the x-axis bit, and we're going to revolve it around the y-axis for the y-axis bit. But let's do the x-axis first. We're going to revolve it around the x-axis, and that is the radius of revolution there. And let's just have a look at what this is. Basically what it is we have a nice little cuboid here, which will be dx by dy, and this distance here will be 2 pi r. And what we then do is we sum up all of these tiny little cuboids across the region about which we are integrating, and that will give us the volume of the solid of revolution. That's the idea of the whole thing. And then basically the volume will be equal to 2 pi times the double integral over the region r, and this is the region about which we're integrating, of all of the r's. That's the 2 pi r there, which is that bit, dy dx, which is this bit here, and that gives us the volume of revolution. So let's do it now about the x-axis. Let's just redraw it. Now the only hard thing, or one of the main hard things about this, is working out what your limits of integration are. So here is y is x squared, here is y equals x, here is our region, here is our little point here, dx dy. This is obviously 0, 0, and this point here is 1, 1. So what we're going to do is we're going to rotate this around the x-axis to find the volume. And so basically what it is going to be, we are going to integrate from x all the way from 0 to 1. So x goes from 0 to 1. And y, I'll do y in a second, but let's just have a look at the volume. So the volume around the x-axis is going to be equal to 2 pi times the double integral. Okay, well, we know the x bit is going to be between 1 and 0. We know this distance here, the radius, is y by definition. So it's 2 pi y, and we'll just leave this and this just for a second, dy dx. That's the double integral. Now all we need to do is just look at the limits for y, and what we need to do is we need to look at where we're entering and where we're exiting. So when we are looking at y, we are entering at this point here, which is x squared, and we are exiting at that point there, which is x. And so therefore, if we are integrating x all the way from 0 to 1, and we exit the y, enter the y x squared and exit at x, enter at y squared, exit at x, enter at y squared, exit at x, then we will cover the entire area. So our limit here is from x squared to x. So now we have that our volume is equal to the integral between 0 and 1, the integral between x squared and x of, 2 pi of y dy dx. And now this is quite simple. All we need to do is first of all do this integral here, and that gives us 2 pi, the integral between 1 and 0 of, well, the integral of y dy is y squared over 2 between x and x squared dx. Remember, we've got to do the second integral, and that equals 2 pi, the integral between 0 and 1 of x, putting x in here, x squared over 2, then putting x squared in here, minus x squared squared, x to the 4 over 2 dx. So now we've got the second part of the double integral to do. The 2 cancels with the 2, so that gives us pi times the integral between 0 and 1 of x squared minus x4 dx, which equals pi x cubed over 3 minus x to the 5 over 5 between 1 and 0, which equals pi, a third take away a fifth, oops, that's not very clear, a third take away a fifth, which equals 2 pi over 15. So we have worked out the volume of revolution around the x-axis as being 2 pi over 15. And now what we need to do is we need to work out the volume of revolution about the y-axis. Okay, so let's just redraw it here. So we have here y equals x. I have here y equals x squared, which also can be written as x equals root y. Again, this is the point 1, 1. Again, this is the point 0, 0. And here we have a little dx dy here, but this time what we're going to be doing is we are going to be rotating it around the y-axis, and so this is the radius that we are going to be interested in. Okay, so what we're going to do this time is, again, we have that the volume is equal to 2 pi times, now what we're going to do this time is we are going to integrate from y equals 0 to y equals 1. So therefore, the limits of the y are easy. Let's just leave for the second the limits of the x. And it's going to be r dx dy, because we're going to do the dx integral first. And r, in this case here, is clearly x, because this is the point x here. So that becomes, so the volume equals 2 pi, integral between 1 and 0, integral, we'll leave those limits for a sec, x dx dy. Now what we need to do, if y is going from here to here, in order to cover this region here, we need to enter at this point here. Well, that point there is x equals y, so our entry point is y, and our exit point is here. Well, that is x equals root y, so our exit point is root y, and that gives us our limit for the internal. And all we've got to do now is do this integral, so that becomes 2 pi, the integral between 1 and 0. Doing this integral here first, the inner integral first, that becomes x squared over 2 between root y and y dy. We've still got to do the outer integral, and that equals, taking that 2 out, pi, integral between 1 and 0, sticking y, root y in there first, gives us y, and then sticking y in there, minus y squared dy, and we're almost there now, equals pi times by, now we integrate with respect to y squared over 2 minus y cubed over 3 between 1 and 0, which equals pi, a half minus a third, which equals pi over 6. So that is the volume of the solid of revolution going around the y-axis using double integration. So now we can actually finally answer our question here. Basically the question, so the volume bounded around the y-axis was pi over 6, and around the x-axis was 2 pi over 15, and pi over 6 take away 2 pi over 15 is equal to pi over 30, which is answer B, which is the same as we got in our previous video, fortunately. So basically, even though this is the same question, it's using a different technique, double integrals, and if you can basically get your head around the limits, i.e. this bit here, where you're entering and where you're exiting, then this is actually probably just as easy as using the disk method. Okay, well, I hope you found this useful and informative. If you have, please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.